Okay. So my goal today is to finish chapter 22 and start chapter 23. Chapter 22 has to do with electric charges and forces, and they do mention the electric field. Chapter 23 is devoted to the electric field. And chapter 23 is just doing some integration to calculate the electric field for a variety of distributions of charges. We'll start with the point charges, the dipole, and then the continuous charge densities. And so there will be some integration. So here's what we did. Just highlights on about electricity. I'm going to do this example in a second. So, what do we know? There are what kinds of charges? How many kinds? Two types. There are pluses and minuses. So charges. Usually the symbol for a charge is Q, right? Either little q or capital Q. The unit for charge, the SI unit is the SI unit is the Coulomb, right? And C for Coulomb. The charge of we said there are pluses and there are minus charges, right? Positive, negative. Electrons and protons are the main carriers of charge, so we'll deal with pluses and minuses. Now, a proton would have a charge of positive. Does anybody memorize that number? 1.602 something times 10 to what power? It's a small charge. Yeah. The one with the 9 we'll see in a second. So it's to the minus 9 Coulomb. For an electron, it has the same charge but negative. It was minus 1.6 times 10 to the minus. I'm sorry, 19. I should say 19. Yeah, not 9. Just 19. Protons, electrons. Then we said charges that are alike, if it's a plus and a plus, or a minus and a minus, they repel. A plus and a minus, or a minus and a plus, they attract. Now, how much is the force between them? What is the magnitude? That's quantified by Coulomb's law. So if you have charge 1 here, and charge 2 here, and they're separated by a distance r, then by Coulomb's law, the force between them would be K, Q1, Q2 over R squared. Another way to write this same thing is to write 1 over 4 pi epsilon naught, and then Q1, Q2 over R squared. So you see here, the only difference, there's a K here, and here there is 1 over 4 pi epsilon naught. Those are constants, and K, actually the book uses capital K, so we'll try to imitate capital K. And it is basically 8.99 times 10 to the 9. So approximately 9 times 10 to the 9. The units will be newtons, meters squared, or Coulomb squared. It's the Coulomb constant, right? Epsilon naught is also a constant. It's they're related. You can put K equals to 1 over 4 pi epsilon naught. So if you know K, you can calculate epsilon naught. It turns out to be 8.85 times 10 to the minus 12. And since it's 1 over, it would have 1 over the units. So Coulomb squared, newton meter squared. Okay, so that's what we basically talked about. I gave you the electron mass, the proton mass, and so on. If we need them, I will mention them again. But for now, that's it. All right. Okay, so I would like to do an example here, just to get some practice. And let's see if we can do it. All right. Yeah. Can I roll the board down? Did everybody get that one? from the book, you have 3 charges on the corners of a rectangle. The rectangle is 5 centimeters this way, and it is 10 centimeters this way. And the question is, find the force on this 3rd charge due to the other 2 charges. So let's see what the 2 charges are doing to this Q3. Notice Q3 is a plus, Q1 is a minus, and Q2 is a plus. So, and I give you the magnitudes. Q1 is minus 50 nanocoulombs, and this one is positive 50, and this one positive 30. Okay. So what would Q2 do to Q3? Attract or repel? Attract, because they're oppositely charged. So I already know that the force is directed along the line that joins them, right? That joins the 2 charges. So it would be this way. That's the force on charge 3 due to charge 2. That's the due to charge 1, I should say. That's the force on charge 3 due to charge 1. Okay? So that's what charge 1 does to charge 3. It would try to attract it. Of course, charge 3 is also pulling on charge 1. But the question is asking about what happens to charge 3. We're asked about the forces on charge 3 due to these other 2 forces, due to these other 2 charges. Now, what does Q2 do to Q3? Repel. Yeah, Q3 is positive. Q2 is positive. Q3 is also positive, so they repel, and that force will be repulsive. So it's in this direction. That's the force on 3 due to charge 2. Okay. All right, good. We drew the forces. Now let's find their magnitudes, and then we will worry about their directions. So first, find their magnitudes. By magnitude means, don't worry about the plus and minus for the charge. Okay? Just find how much is the force. Just some number, positive number. And then you can worry about the direction of the force, and you can insert those pluses and minuses. So that's a good strategy. So the force on 3 due to charge 1, according to Coulomb's law, it's K, Q3 times Q1, right? The product of the 2 charges, since I'm talking about 3 and 1, so 3 and 1, divided by the distance between them. And so let's see what the distance between them, I would just call it for now the distance between 3 and 1, R13 squared. Okay? So that we will plug in the numbers now. K is, I will put 9 times 10 to the 9. Q3, how much is Q3? Good, yeah, I don't want you to passively listen to me, I want you to actually look at it. So 30 nanocoulombs, yeah, thank you. So 30 nanocoulombs, nano means 10 to the minus 9, so 30 times 10 to the minus 9. And then, how about Q1? Negative 50, right? So since we want just the magnitude, I'll put just 50, positive 50. We will worry about the direction in a moment. So 50 times 10 to the minus 9. Now, how far apart are they? They're 10 centimeters apart. So 10 centimeters is 0.1 meters, but don't forget, it says r squared, so you have to square r squared. Okay, so let's get the magnitude. We will worry about the direction again in a second. So let's get that magnitude. By the way, 10 to the 9 times 10 to the minus 9, so that's convenient. You can cancel one of these two here. So you'll have 9 times 30 times 50 times 10 to the minus 9 over 0.1 squared. I would wait for you to give me an answer, and then we will continue.
I got 0.00135.
0.00135. Thank you. So that's 1.35 times 10 to the minus 3. Or let me keep it this. Yeah, let me put as a power of 10. So it's easier. So 1.35 times 10 to the minus 3. Thank you. 1.35 times 10 to the minus 3. It's a force, so newtons, right? we will, again, I would worry about the direction in a second. Yes, technically Q1 is negative. Technically this one will have a negative sign, but we'll worry about the direction in a second. So for now, I'm just absolute value of everything, okay? Now let's do the force on 3 due to charge 2. Well, it would be K, charge 3 times charge 2, divided by the distance between charge 3 and charge 2 squared, equals K, as usual, is 9 times 10 to the 9. Charge 3 is 30 times 10 to the 9, times 10 to the minus 9. And then charge 2 is 50 times 10 to the minus 9, divided by the distance between them squared. So what's the distance between them? Well, it's the diagonal.
11.18.
Yeah, from here to here, you said 11.18?
Yeah.
So diagonally, this is the distance between charge 3 and charge 2 is 11.18 centimeters, right?
Yes.
Which is 0.1118 meters. So in here, you would have 0.1118. So don't forget the square. If you see a mistake, please let me know. It seems right. Okay. Yeah, I mean, the diagonal should be longer than the side. So let's do that. Again, 10 to the 9, 10 to the minus 9 cancels, and we should get a smaller force.
0.00097, or 9.7 times 10 to the negative 4.
Yeah. Like this, 9.7 times 10 to the minus 4?
Yeah.
Okay. Anything after the 7? Anything
No.
significant? No? Okay.
6.9.
Okay, so I would put it this way. I would put, since this one is times 10 to the minus 3, I would also write this one as 10 to the minus 3 and put 0.97. Okay, so that later when we add, they all have the same values. So we can easily calculate. Okay, we got their magnitudes. Now we would worry about their directions. Okay, so let's worry about their directions. So first, the force on 3 due to 1, does it have an x component? And does it have a y component? The force on 3 due to 1. So let's look at it. The force on 3 due to 1. By the way, here is my coordinate system. I forgot to draw. Here's x, here's y. Okay. So the force on 3 due to 1 points straight down. Which direction is that?
Y direction, negative y.
Negative y. So it does not have an x component, right? It doesn't have an x component. So the x component of this force is 0, and its y component is, well, it's entirely in the y direction. So it's this number, but with a minus sign. See, I put the minus sign on by myself, so we do that. So minus 1.35 times 10 to the minus 3 newtons. Now let's look at the force on 3 due to 2, x component, and the force on 3 due to 1, the y component. Let's look at it. The force on 3 due to 2 points in this direction. So this direction, it points upward, so that's a positive y, but it also points left. So that's what kind of x? Plus, minus? Negative x. So the x component would have a minus sign, the y component will be positive. Now the x component would be in this direction, so I have to multiply by the cosine of this angle. Now what is that angle? What's this angle? Call it theta. Well, it's the same angle as theta, right? Yeah. And what's the cosine of it? Oh, cosine is adjacent over diagonal, or over the hypotenuse, right? Adjacent over there. So that's the cosine. So it will be 5 centimeters, which is 0.05, divided by the diagonal, which is 11.18 centimeters. So you can put 5/11.18, centimeter over centimeter, so they cancel.
63.43?
Oh, okay, the angle?
Yes, for the.
Oh, you found the angle, thank you. So, yeah, why not find the angle then? So
Yeah,
let's
sorry,
find
we're
it.
doing it.
So, so I know that, you said cosine of theta will be, this adjacent, which is 5 centimeters, over the hypotenuse, which is 11.18. Again, it doesn't matter because centimeter over centimeter cancels, and therefore if you do arc, or inverse cosine, you will get theta equals to, you said 60, how many degrees?
63.43?
63.43 degrees, thank you. So why not use that? Okay. So, it will point in the negative direction, and it will be equal to the magnitude of the force, which is 0.97 times 10 to the minus 3 times the cosine. So 0.97 times 10 to the minus 3 times the cosine of this 43.43 degrees. And then for this one, it's positive, and you have 0.97 times 10 to the, minus 3, right? 10 to the minus 3. And then sine. For the y, would be the sine. So 63.43 degrees. Make sure your calculator is in degree mode, by the way, if you're using degrees. So let's get these numbers. So this one would be negative what?
My primary was harder than my eighth grade.
Negative 4.34 times 10 to negative 4?
Okay, so negative 4.34, so 0.434 times 10 to the minus 3.
Minus 4.
And if I put the decimal here, it would be minus 3.
Oh, sorry, I didn't see.
Does that
Yeah.
sound good? Okay. And then the other one, I'm trying to put everything times 10 to the minus 3, so I can have easy time adding things later.
I got for the other one 8.67 times 10 to the negative 3. Or 8.68, I guess you could say.
8.68?
If you're rounding up, yeah.
Let's say
Yeah.
0.97, so it would be 0.868, right? Oh, wait, I didn't have it. Okay.
Every
Yeah.
school.
Okay, so
Not the school.
0. Maybe we should have worked with 10 to the minus 4 then. That's okay. So now, to find the net force, you will add the x components together and you add the y components together, and then you find your vector. So I'm going to roll this up and use the other board. Can I erase this, by the way?
Can I take pictures?
Yeah. Yes. Yeah.
Quiz this coming Monday, Tuesday.
I think next week we don't have a quiz on Tuesday.
We have class?
Huh?
We don't have a quiz.
No quiz, but we do have class. Yeah. But double check with the syllabus. In my memory, we don't have a quiz. Because the next quiz will involve 2 chapters or so. I don't think so, yeah. Did everybody get this one? Can I erase here? Okay. So let's erase it. So the net force. So the net force, the x component of the net force will be the net force on 3 due to 1 x component plus the net force on 3 due to 2 x component, right? You add the components. And the y component of the net force will be the F31 y component plus F32 y component. So let's do that. Let's add the x's together. The force on 3 due to 1 x component is 0, right? It's 0. And this one is minus this. So 0 plus this will just be that. So it's negative, negative 0.434 times 10 to the minus 3 newtons. Now this one, you add the y components. So this one is negative that number, and the y component of this one is positive that. So add them. So
I got negative 0.482.
for this one, okay. Let me write this. So you have minus 1.35 times 10 to the minus 3, and then plus 0.868 times 10 to the minus 3. And can you please quote me that number again?
Negative 0.482 times 10 to the negative 3.
Like so, right? So now we're ready to write the net force. Therefore, if you like to write it in vector notation, the book wants you to write it in vector notation, so let's write it. So it will be this minus 0.434 times 10 to the minus 3 I hat, and this is the j hat. So minus 0.482 times 10 to the minus 3 j. Okay. Now they want you to also find the magnitude of this net force. You know the procedure, find net force, find the components first, and then find the magnitude. Magnitude, you square the x, you square the y, and take the square root. So when you square them, to make life easy on your calculator, if you square this, it has 10 to the minus 3, and this one has 10 to the minus 3. So you can just factor that. So I would just square this 0.434 squared, and then 0.482 squared, take the square root of those, and then times 10 to the minus 3 at the end. Because it's going to be 10 to the minus 3 anyways. It just factors out. You're going to square 10 to the minus 3 and then take its square root. It's going to be 10 to the minus 3. In other words, the net force magnitude will just be, when you square a negative number, it would be plus, and you just 0.434 squared plus 0.482 squared, square root, but then everything times 10 to the minus 3. That's easier to write on the calculator. So the net force, let's find it.
I got 0.65 times 10 to the negative 3.
Like this, 0.65? Okay, I will just write that. And, so that's the force. Now what angle does it make? Now it will be, the force points this way, right? That's the force. The net force, in other words, the net force points that way. So it's makes this angle phi here. Okay, so phi will be the tangent of phi will be the y over the x.
I got around 48 degrees.
40 something. Okay, yeah. Yeah, I mean they're almost equal to each other, so it would be in the 40s probably. If they were equal, it would be 45, exactly. So let's write it. So phi, the tangent inverse of the y component over the x component. So that's 0.482 over 0.434. And again, why didn't I bother to write times 10 to the minus 3? It's going to cancel anyways, yeah. And I heard it's 48 degrees. So it makes 48 degrees with the x, with the negative x axis. Let's see. Yeah, I mean the y is larger than the x slightly, so it's more open toward the y. So yeah, it's more than 45. So it looks good.
So if you were to as an angle, would it be like 132 or is 48 okay?
Oh, you can say it different ways. You can say 48 degrees with the negative x-axis.
To the negative, okay.
If you want to measure it from here, you can say it's 180 minus 48, which is, you said 132?
It's 132.
132, yeah, with the positive x-axis. Some would say, what is it, 48 degrees north of west.
Okay,
Yeah.
vectors.
So, yeah, yeah. But, yeah. All right, That's that. I would like to go on to the next topic, which is the electric field. So the electric field, to talk about a force, how many charges do you need to have a force? 2 charges, yeah. So because if you have a charge by itself, it doesn't exert a force on itself, it exerts a force on other charges. So what if you just have 1 charge present? What does it produce for you? Does it just not do anything? Well, it produces what's called an electric field, and as soon as you put another charge in the electric field of this earlier charge, that next charge will experience a force equal to the product of the charge times the electric field. And I will write all that stuff down. So here's what's so the electric field now is part of chapter 22 and it's also part of chapter 23. So for the rest of the day, we'll just talk about mostly electric fields. So suppose I have a charge here. Here is Q. And here is another charge, let's call it Q prime, right? Q prime. And let's say they are a distance r apart. The distance r apart. Okay? So according to Coulomb's law, by Coulomb's law, the force between these 2 charges is what?
K Q1 Q2 over R squared.
Yeah, K Q1 Q2 over R squared. Yeah. So it's K Q1 Q2 over R squared. I would also write it as 1 over 4 pi epsilon naught Q1 Q2 over R squared. And since I named them Q and Q prime, I'll just put Q and Q prime over R squared. Over R squared. Okay. Yeah. So I just wrote Coulomb's law. And from now on, most of the time we usually write 1 over 4 pi epsilon naught. Sometimes we write K also. But they're exactly the same. The reason we prefer this one, you would see it when we have charge distributions. The 4 pi is there to be cancelled later. So it's defined this way so that you cancel the 4 pi and you end up with an epsilon only. Okay, so now this portion, we're going to call it the electric field produced by Q. Okay, so the electric field produced by Q, so let me call it E. So E for electric field. E for electric field is just Q or 1 over 4 pi epsilon naught, and then Q over R squared. Electric field produced by Q a distance r away. So in other words, now the force on Q prime is equal to all this stuff which we defined as the electric field, right? All this stuff in orange here is called the electric field, so E times Q prime. Okay. All right. Is that clear? So we just defined this quantity called the electric field. Now, how does the electric field is a vector, because if I were to, let's say, if this charge is a plus and this charge is a plus, it will experience a force in that way. It will be repulsive, right? So the electric field will also point in that direction. If it points away from positive charges. And if this were a negative charge, well, if you have a vector that points this way, and now I multiply that vector by -1, what happens to the vector's direction?
Opposite.
It becomes this way, it flips. So here is the, here if I have a plus charge, we can think of it as creating an electric field. Basically, every point in space would be assigned some vector. Okay, some vector. And the electric field, if we are a distance r away, the electric field always points away. So you can think of every single point, everywhere you are, there is an electric field due to this charge. All of them are electric. That's the electric field produced by this charge Q. If I put a Q prime in here, it will experience a force. And the force on it will be the Q prime times E. Okay. Q prime times E. Seems a little convoluted. I mean, why would you use the electric field when you already have Coulomb's law like this? But it would be helpful to think in terms of fields, as we can see, but rather than just forces. Okay. Does that sound? Yeah.
You just wanted to make sure I got it. So the force Q prime times E is the force that you're experiencing all around that charge, like in every direction.
This one.
Yeah, the force. Yeah, so like
The
the
force,
force. It's just like the force all around
Oh, the
project.
force would be experienced, if I put Q prime, it would experience a force right here.
Oh,
But the
okay.
electric field is everywhere.
Got it. Okay.
Yeah.
But it's just okay. That makes sense. Okay.
Okay. So if I were to take this now Q prime and place it here,
Cool.
it would experience another force, right?
Right.
And that force will equal to whatever the value of the electric field here is times the charge, Q prime.
Okay.
Yeah.
That makes sense. Thank you.
Yeah. For now, I like to think of it this way. We'll get used to the concept of the electric field. For now, I like to think of it this way. In order to talk about a force, you need two charges. But if you have just one charge, what can you talk about? So the way I like to think of it is like, we don't want to be just not say anything. So the electric field is a way to talk about something, even if you just have one charge and you don't have a second one, okay? If you want to think of it that way. So, all right, so that is that. This is the concept of the electric field. And what would the units of the electric field be based on this? Newtons is the force, QE. So Q times E has to produce for me newtons. So what should E have? What kind of units?
For now, what am I saying, newtons over Coulomb?
Yes, units the charge, probably.
Yeah, so it's a charge. Force, if I divide F by Q, I get E. So F over Q is E. So it's newtons per coulomb. Yeah. Force per unit of charge. Force per unit. So the units would be newtons per coulomb. We will have other units for it, other convenient units also. When we talk about voltage, it will be a volt per meter. So we will, yeah, it's equivalent, but also convenient. Okay. Let's see. So now, okay, we want to calculate the electric field due to a collection of charges. We will start by the electric field due to a dipole. So, before I get to that, let me emphasize, electric fields always point away from plus charges. And by away, just away, depends where you are, right? And then if you have a negative charge, electric fields always point toward the minus charges. They point toward minus charges and away from pluses, which makes sense. If you have a vector that points away, if this becomes negative, you will have the negative of that vector, so every arrow here will flip and point towards. So another way to say it, electric fields emanate or start from pluses and they terminate in minuses. They end in minuses. Okay. All right. So let's start with the first one is a dipole. The electric field of a dipole. A dipole means two poles. Dipole. One pole. The polarity of a charge is whether it's plus or minus. So a dipole will have a plus charge and a minus charge. So if I have a plus Q and a minus Q, the total charge is how much?
Zero.
It's zero. If they're at the same spot, then the total charge is just zero and they don't produce an electric field because the net charge is zero. But if they're not quite at the same spot, then the electric field will not cancel and they will produce some electric field. And I would like to calculate that at different locations. Okay, so here is, our first calculation with electric, fields. So here is a dipole. Let's place it on the XY plane. Here is X, and here is Y, okay? And I'm going to put my dipole here. I'll put a plus charge here. Put it with orange, with the plus, and I put a minus charge right here. I'll also choose maybe orange again. Orange, okay? Both of them, this is positive Q, and this one is negative Q. They have the same magnitude, but different. One is plus, one is minus. How far apart are they? Let's say the distance between them is S. So the distance from here to here is S over 2. And the distance from here to here is also S over 2, right? And, sorry for the choice. Usually books use D, but our book uses S. And S looks like 5 sometimes. It's S.
It's
not 5. Okay. So the first question is, what's the electric field along the axis connecting the dipole, on the axis of the dipole? What's the electric field? So let's say we're here. What would the electric field be? Let's say we're here. From here to here is Y, right? The distance Y from the center of the dipole. So what is the electric field? Now, let's remind ourselves, what do positive charges produce electric fields away from them or towards them? Away from them. Okay, so we're looking at this point here. Let's make our y-axis a little bit longer so it doesn't come in the way. There's the y-axis. So the positive charge will produce an electric field away from itself, right? I would call it the E plus, meaning the electric field due to the positive charge. And the electric field due to the negative charge, what do minus charges produce? Electric fields in what direction? Towards themselves. So towards, if you're at this point and you want to go toward the negative charge, you go this way, right? That's towards. So that's the electric field due to the minus charge. So they one of them produces an electric field in the positive y direction in this case, and the other one produces an electric field in the minus y direction. They point along the same axis, but one is this way and the other one is this way. But there would be a net field, because you see the plus charge is closer and the minus charge is farther. So the electric field due to the plus charge will be slightly larger than the electric field due to the minus charge. Because here's the formula for electric field. It's 1 over 4 pi epsilon naught, that's a constant, Q, okay? But then you have to divide by the distance from the charge to the position where you're calculating the electric field, distance squared. So if R is larger, then it's would be a larger. Okay.